The flow in is 10 liters per minute, so that's V naught. The initial concentration of A is 0.3 moles per liter. And the initial temperature is 283 Kelvin, or 10 degrees Celsius. The volume of the CSTR is 10 liters. And then, of course, we have coming out concentrations of A, B, C, and it's all reacting at some temperature. And the problem is asking us to find all four of these parameters for these inlet conditions, assuming that you're also given thermodynamic and rate data. AKA, you're going to be given delta H of reactions and rate constants. All right, so how do we start the problem? Design equation. What does that look like for multiple reactions? Is it this? No, right? That's what we use for one reaction. So what do we do here? No, we don't want to work with conversion. We have two reactions going.
I'm sorry, you said reaction, sorry.
No, we don't really want to, you can, but yeah.
Do you do like a mass balance for each one?
Yeah, we want to do a material balance for each species. All right, so let's start with A. And so for A, you get that the volume is equal to the flow rate in minus the flow rate out divided by the rate of A. And it's important to point out here, what rate is that?
Rate.
The net rate, right? It's always been the net rate. In multiple reactions, it's even more important to think about it because even if all the reactions are irreversible, a lot of times the multiple reactions, one of them is consuming a product or something like that. Now in this case, we don't have that, right? There's only one reaction involving species A. What is the material balance for species B? What's the flow into the system of species B? What's the flow out? FB. And then what's the rate? Is that right? But is it negative RB or is it just RB? It's still negative, right? And then you'll see that that's often the first thing you might write down, right? Is because you're just going to have a negative over a negative, so that cancels out. So this kind of makes more sense in your head. Flow rate goes up as rate goes up, right? For a fixed volume.
And the rate of B has to be positive, right? And no matter what, it'll have to be positive overall. Because there's nothing starting with it.
That's a variable on which
I'm not sure what you mean.
The rate of B will, the net rate of B will always have to be positive if it doesn't start from the B, right?
I mean, for an irreversible system, yeah, because the rate of 2 is going to be 0 if you don't have any B. So is that what you mean? I think you're just saying that.
I think I'm just trying to say, like, because B is being generated from nothing, essentially, the rate of B has to be positive. You can't do that, because then you have a negative volume otherwise.
At the end of the reaction, though, B's going to be consumed to C.
Well, I mean, the net rate would have to be positive.
So you guys are, all right, so we've got a few things going on here. The net rate in a CSTR is going to be positive. Yes. You're right, you can't end up with a negative volume. What you're thinking of when you're saying at the end of the reaction, B is going to be consumed. Hear the phrase end of the reaction. So if you mean end in terms of time, that's a batch reactor. If you mean end in terms of the end of a reactor, that's a PFR. Does that make sense? So you're right, that in a PFR, you can accumulate B and then consume it. And in a batch reactor, you can accumulate B and then consume it. But a CSTR can't operate that way. It's all occurring at one condition, right?
But couldn't be reacting as fast as it's being generated? Like,
Yeah, so the rate can be very close to zero.
yeah, I was gonna say. could be
Right,
zero.
but it can't be negative within a
Yeah.
CSTR. It can be negative at portions of a PFR, and it can be negative at certain times in a batch reactor. Okay.
Why did you write net there?
To remind you,
Like, what would happen if it was parallel?
what would you mean?
It is those
I mean, you could have this is a valid question for a multiple reactions problem, right?
Okay, so those equations still don't change.
No,
Okay.
they're the same. Now the rate of B is going to be the rate of B produced here and consumed here. Notice it's the same. I just wrote it in 2 steps. The rate of A is going to be consumed in 2 steps, right? And if I make one of these reversible, so the point is that whenever you write down the rate of consumption or production of a species, you need to look at every single reaction and the reverse reaction if they're reversible reactions. So yeah, what is the net rate of consumption of A? So how many reactions do we have in this system? I think it's nicer sometimes to write them as two steps. All right, so we have 2 reactions, right? How many involve species A? Just the first one. And so I'm going to write this as minus 1R minus R1A. So what do I mean by this versus this? Yeah, this is just the amount of A consumed in reaction 1. Remember, look at your energy balance equation, right? Now the rate has 2 subscripts. All right, and so in this case, what is that equal to?
But you define A as the consumption of A, so wouldn't that be a positive thing?
Since you defined it as negative RA, it would be
It would be
positive R.
positive R1A. Since you divided RA as the consumption, you defined it as.
But I didn't say that this was production or consumption. This is the same thing. This is still production. RA is production, R1A is production.
Oh.
So the sign has to match.
Oh, okay. Fine.
Yeah. All right, so what is this equal to?
Negative K.
K1A CA, which is also equal to K1 CA. Now this one, it's not very interesting. All the stoichiometric coefficients are 1. The second problem that we're going to do, that's not the case. And we'll revisit this K1A versus K1 thing again. We've done it a few times now, but we'll do it again. Okay, now what do we get for B? R1A, but we're going to put 1B to start. So we're just saying how much, we're looking for the total amount of B produced. So the first thing we're going to do is have the amount of B produced in reaction 1 plus
Negative R2.
and so then with K's, we have K1A, CA, minus K2B, CB. And again, because all the stoichiometric coefficients are 1, what you're more accustomed to seeing is me to write that. This is K1 times concentration of A minus K2 times concentration of B. Okay, what about stoichiometry? So that's our material balances are written, rate equations are written. What do we do for stoichiometry?
We don't need one
Hmm?
C is the same, right? Well, it's the same design equation.
Yeah, we could have written. Yeah, I mean, we can do that. So. And so then what's the rate for C? Just the amount of C produced in the second reaction, because that's the only reaction where C is produced. K.
2C.
Still B, because you define rate constants based on the reactants.
But again, since we're simplifying all of it.
Yes. It's going to be the same as K2 concentration of B. Again, when we do the second example, we've got some stoichiometric coefficients. It'll help clarify some of the differences that we're seeing here. Okay, so the stoichiometry section is what? How do we relate flow rates to concentrations for CSTR? Concentration of a species is equal to what? Flow rate of that species divided by the volumetric flow rate. Does the volumetric flow rate change for this system? Why not? It's not isothermal because it's liquid. So you get flow rate over the initial volumetric flow rate. That's it. Stoichiometry is pretty simple for a liquid phase reaction. All right. So let's combine for species A, and what we get is the volume is equal to the volumetric flow rate, the initial concentration minus the concentration divided by K1 CA. And we can rearrange that now to solve for the concentration, since that's what we don't know. Here we already know the volume, so it's kind of